Alright guys, so this is the one of the extra lectures on graphing the first and graphing the function based on the first and second derivative test that we did not get to in class. So let's jump right into it. If you watched the first video, I just worked through all these steps, so that's essentially what I'm going to do, keep it as short as possible. So here we go. Alright, whoops. So here we go. First we're going to do the derivative then test. Sorry, that's 1 over x squared minus 4 minus 2. So I apologize for these. It didn't copy and paste well there. So here's the function. Alright, that's squared. Now we're doing the derivative to this function, which we know how to do. It's simply quotient rule. Here's the top, here's the bottom, right there. Here's the bottom, and we're going to do a quotient rule, and that's just plain old constant. Okay, that's a plain old constant. So here we go. The derivative of the top is 0 times the bottom, x squared minus 9. Minus the derivative of the bottom is 2x, or sorry, x squared minus 4. That's a 4. Let me double check. It's 4, right? Yes. Alright, so minus 2. 2x is the derivative of the bottom. Okay, 2x times the top 1. So over the bottom squared, which is x squared minus 4 squared. So let's simplify this. Oh. And this goes away. It's negative 2x over all that good stuff. Alright, so here what we have to do is we have to find out where the derivative is equal. We have to find the critical points, okay, which is where the derivative is equal to 0 and where the derivative is undefined. So equal to 0 would be the top. And undefined, sorry, equal to 0 would be the top equal to 0. Undefined would be the bottom equal to 0. Is Aiden out there yelling at everybody? That was on video, wasn't it? Oops. Oh well. Alright, so equal to 0 would be the top equal to 0. Undefined would be the bottom equal to 0. So negative 2x is the top equal to 0. Alright, so x is equal to 0 there. That's a critical point, because it's where the derivative is 0. Okay? Now also, for the bottom equals 0, you have x squared minus 4 squared equals 0. Alright, square root, square root. Square rooted, cancel, cancel. You have that. Y'all know how to solve that. And then bam, bam. So x is equal to positive and negative 2. Okay? So what we have here is we have our critical points where they are undefined, and where the derivative is undefined, and where the derivative is equal to 0. Okay? Alright, so cool beans. Okay, so we need to go ahead and test this. So let's go ahead and get about the business of testing and draw a number line here. Okay, negative infinity to infinity. Alright, so we want to put all our critical points. So we got 0, CP, negative 2, CP, and positive 2, CP. Alright, so testing f prime of negative 3. Now know this, guys. Know this. Okay? When you're plugging in the derivative, take, like, that's squared. Okay? That's always going to be positive. Never going to be negative. So we're just plugging in the top, essentially. So plugging in the top, 2 negatives gives me a positive. Alright? So this is going to be increasing on the interval negative infinity to negative 2. And here, f prime of negative 1. Still 2 negatives make a positive. So we're going to be increasing on the interval negative infinity to, not negative infinity, negative 2 to 0. And then we're f prime of positive 1. Positive and negative make a negative, so now we're decreasing. Okay, on 0 to 2, and then f prime of 3, still negative, still decreasing on the interval 2 to infinity. Alright, so there we go. There you have it for number 1, or letter A. Deriving and testing. Now we gotta go about the business of doing the second derivative and testing. So here we go with the second derivative. In order to do the second derivative, first you need the first derivative, so we have it. So we're at B. F prime of x is equal to negative 2x over x squared minus 4 squared. So now we're going to do the derivative to that. D over dx of all that stuff. So I'm going to work a little bit sideways here. So that's going to be f double prime of x, the second derivative, is equal to, once again, this is a quotient rule. Okay, here's the top, here's the bottom. But on the bottom you have a chain rule, don't you? So what we're going to do, we're going to take the derivative of the top, negative 2. When we take the derivative of the bottom, we end up with a chain. Okay? But just a chain right here. So only a chain right here. So don't put chains all over the place. It's just one chain rule. Alright? So 2 x squared minus 4 times 2x. Alright? I think gotta get something that goes over that. Orange, I guess. Alright. Alright, derivative of the top times the bottom minus the derivative of, oh my goodness, I just messed that up, didn't I? I'm so sorry. That's the derivative of the top times the bottom. Oh my goodness. Times the bottom. Woo. So x squared minus 4 squared minus, now the derivative of the bottom, chain rule. This is now a chain. 2 x squared minus 4, subtract 1, that's 1 in the exponent times the derivative of the inside 2x, times the top. The top is negative 2x. Well, that's a mouthful. Now the fun part is we get to square the bottom and then we get to simplify. Alright, so we have x squared minus 4 to the second power. We have that squared. These two negatives multiply. Okay. Or sorry, these two exponents multiply, and then we have our final result, but we have to simplify it. So I am going to go ahead and start simplifying. I'm going to FOIL that out. So still have negative 2. and then x to the fourth power minus 8x squared plus 16. That was just me foiling this out right here, so take a look. That was x squared minus 4 times x squared minus 4, and that would have led me all the way to that. Alright, and then minus, I'll just go ahead and multiply these and then distribute. So we end up with 2x squared minus 8, and that's negative 4x squared. And of course the bottom, we multiply the exponents, so we end up with x squared minus 4, with these exponents multiplying to the fourth power. Now we still have to simplify the top, so let's continue at the prime of x. Why do we have to simplify the top? Because there's no way to set this equal to 0. You're going to have to simplify it anyway, so you might as well get your butt going, right? So simplify, simplify. We multiply, we get negative 2x to the fourth power plus 16x squared minus 32 minus, now I get to distribute this reverse-wise. This is negative 8x to the fourth power plus 16x squared. Okay. Which these end up being different signs anyway, because two negatives here, get rid of that. That makes a positive, and this makes a negative. So we end up, oh, I forgot my bottom. So we end up with 6x to the fourth power. That those cancel. Plus, I already got those. 6x to the fourth power minus 32. That was easy. Not 36. All over x squared minus 4 to the fourth power. So this all ends up pretty easy. So now we want to find all the inflection points of the second derivative. Okay? We want to find all the inflection points of the second derivative. Now, you have to do the top and the bottom on this too. We did not discuss this in class, okay? But yes, you have to do the top and the bottom on this too. So when we do the top, we get 6x to the fourth power minus 32. Don't start factoring. We can isolate x. There's only one x, so we can isolate it. So 6x to the fourth power equals 32. Divide x to the fourth power equals 5 1/3. 5 1/3, or 16 over 3. And then the fourth root, or actually, take that back, I do not like square roots, to the 1/4 power of each. And I guess I can use a decimal here. I'm not a fan of decimals, but we can do it. Okay. So, my brightness went down for some reason. Alright, so (16) divided by 3 comma caret to the 1 divided by 4th power. Let's see what we get. 1.5919 1.520, because it rounds. Alright, 1.520. Okay. And that's plot positive and negative because you're essentially taking a variation of the square root. Any even root, the 1/2 power, the 1/4 power, you need positive and negative. So plus and minus 1.520 Alright? Alright, cool. Now we set the bottom equal to 0, and we're going to get a little bit of the same thing, guys. So x squared minus 4 to the 4th power equals 0. You know, raise both sides to the 4th power here. Raise both sides to the 4th power. Well, that's just 0. Cancel. X squared minus 4. X squared equals 4. X equals positive and negative 2. Okay? So, alright. Let me gear down a second. Going back and checking some work. Making sure. Alright. Interesting. Okay, alright, so let's keep moving on. We've got these points, we've got our essential points here that we need. I'm just going to go back and check my work because I have a sneaky suspicion here. I'm pretty sure everything's good, but you never know. Alright, I'm just going to go with my gut. Say it's all good. Okay, so now we need a test. Okay, so let's test. Let's plug it into the first derivative. And I know what you're thinking, oh my gosh, it's already been 20 minutes. But I'm working as thoroughly as I can, and there's simple concepts here. We're doing the same thing every time. It's just taking us a lot longer than we would enjoy it to. So sure we would all like for it to not take as long. 1.520, negative 1.520. Alright, so we have to test for concavity everywhere here, okay? So we have to do f prime of f double prime negative 3. Now f double prime negative 1.6. F double prime of 0. F double prime of let's see, 1.6. And f double prime of 3. Alright. Still have that sneaky suspicion. Alright, right here when I had negative 2x to the 4th power, for some reason my computer is messing up here. Negative 2x to the 4th power, and negative 16x squared, okay, no, I'm sorry, positive 8x to the 4th power, now that's totally legit. Did I mess up somewhere in my derivative? Sorry guys. Alright, so I just thought that maybe these two values were extraneous values, but they seem to be good. So, like I said, you keep plugging along here. Let's plug it in the second derivative. Alright, so we know the bottom is positive, right? You know the bottom is positive, so you're plugging in negative 3 to the top. Alright, so 3 squared is 9, and times 3 is 27, times 3 is 81, times 6, well that's going to end up being positive. So it's concave up. Alright, and then f double prime negative 1.6, I'm going to have to use my calculator on that one. And here it wouldn't be a bad idea to, I'm going to show you again, use your function value, right? So I've got this, and I've got this one highlighted. so that I know I'm plugging it into the original function. But instead of the original function here, I'm not plugging in the original function, I'm plugging it into the second derivative. Alright, so we have to create a new second derivative for y. So I'm going to plug in 6x caret 4 minus 32 divided by parentheses x squared minus 4 in parentheses caret 4 down to the regular in parentheses. And so you see what I got right here. Alright, this is the one that I'm looking at right here, because this is the one that's highlighted. Okay, so I'm looking at that second derivative. Alright, I'm going to go ahead and do second, calculate, value, just to make it easier on myself, okay? So there's my second derivative. It's kind of funky. Alright, so I'm plugging in negative 1.6. Alright, I get a positive value. Very good. Alright, so let's go back. Alright, right here is positive. I could get there. You know what this means? That means that is not an inflection point, because it's concave up to concave up. Alright, right here, now I've got to test what 0 is. That should be easy. Yeah, that's going to be positive, isn't it? Or no? Is it going to be? No, it's going to be negative, because that becomes 0, and that's negative, and that's always positive. So a negative and a positive make a negative. So here it's concave down. Alright, let's test this. I have a sneaky suspicion it's going to be the same as the other one. Alright, so let's do the same thing. Second, calculate, value, x equals 1.6. Yeah, 1.7. It's positive again. Okay, so positive. Alright, so let's go back. Alright, positive, concave up. Alright, and then let's test 3. I'm just going to plug 3 in. You can kind of see from the graph, but I'm not sure. Let's see. So I can calculate value 3, 0.7264. So yeah, that's definitely positive. So, alright, we're done with the test here. And I'm going to wait until the very end to write all my intervals, okay? Because I've spent a long time on this already. So here we go. Working back up, we did the second derivative test. We got that good. Now we're going to get the points of extrema. Now know the points of extrema only refer to the critical points. So let's just look at the critical points. Well, critical points are here, here, and here. So negative 2, 0, 2. Alright, so C, we want f of 2, negative 2, and then f of 0, and then f of 2. Alright? Well, when you plug them in the original function, let's take a look at the original function because I don't have it. Alright? I'll rewrite it. Alright, the original function was f of x equals 1 over x squared minus 4 minus 2. Well, if you plug in these two, you get undefined. Alright? It's okay for a critical point to be undefined. Alright? It doesn't always have to be extrema. Okay? Now f of 0 ends up being negative. Alright? Well, you plug in 0, you get negative 1/4 minus 2. Alright? So 0, negative 1/4 minus 2. So that's negative 2.25, or yeah, let's go with that, negative 2.25. Now, what is that? Go back to your sign chart. Alright, the derivative went from positive to negative, so it has to be a relative minimum, or relative max. Now these two poor little guys are just neither. Okay, Okay, now, so, alright, going down to D. Alright, so that was easy. That took a lot less time than A and B did. Give the x and the y intercepts. So let's go ahead and do that. We have the original function. Alright, so D, x intercepts make y 0. So 0 equals 1 over x squared minus 4 minus 2. So 2, add 2 to both sides. 2 equals, 2 equals 1 over x squared minus 4. And then I can multiply both sides by x squared minus 4 coming up here. So that's 2 x squared minus 4 equals 1. Okay, and all I did was this. Cancel. Alright, now divide. You get x squared minus 4 equals 1/2. And then add. You get x squared equals, that would be 8 over 2 when you add it. So 9 over 2. So x equals, you square root both sides. X equals 3 over the square root of 2. Okay? And you don't have to rationalize positive and negative, by the way, I'm sorry. You don't have to rationalize this, okay? You leave it. Just leave it alone. Alright? And you can write the approximate value if you want, but you don't have to. Alright, the approximate value of, let's look at my calculator here, see what it says. Alright, 3 divided by the square root of 2. 2.121. Approximately. Alright, so it's approximate. But anytime guys, anytime you're caught between choosing to use an approximate value or using a fraction value, choose the fraction value. Just know that what is approximately so you can use common sense. Alright, so next, let's do our y-intercepts, make x 0. And so, y-intercept, you would do f of 0, plug in 0 for x, 1 over, negative 1 4, minus 2. Alright, so, when did I already do that? Okay, yeah, I already plugged in 0 once. So yeah, f of 0, we already plugged in 0 already. It's a negative 2.25. Okay, cool beans. So we found that. Now let's go up. Alright, give the x and y intercepts, state the horizontal or asymptote or slant asymptote. This doesn't have a slant asymptote, but it does have a horizontal asymptote. Here's how you find horizontal asymptotes. We're going to use it the calculus way. The calculus way of finding a horizontal asymptote is the limit of f of x as x approaches infinity, or negative infinity. Alright, so let's first do this one. Oh, sorry. Let's first do this one. Alright, so let's do the limit of the function, which is 1 over x squared minus 4 minus 2 as x approaches infinity. Okay? Well, that is going to end up, let's do the direct sub of infinity. Let's do the direct sub of infinity, so limit as x approaches infinity equals 1 over infinity squared minus 4 minus 2. Well, this goes down to simplify, because you know if infinity is on the bottom of the fraction, that doesn't matter. So it ends up being number over infinity squared minus 2, which essentially is 0. So limit as x approaches infinity is equal to 0 minus 2. So the limit as x approaches infinity equals negative 2. Now, you probably already knew that. You didn't have to do that much work. But I'm just saying, I'm just, showing as much work as possible, okay? Alright, so, and you know what? It doesn't matter if this was infinity or negative infinity because it becomes 0. So you automatically know the limit as x approaches negative infinity of f of x is going to equal negative 2 as well. So therefore, alright, that's kind of rough. Therefore, because the limit of f of x as x approaches negative and positive infinity equal negative 2, y equals negative 2 is a horizontal asymptote. Alright, cool beans. So, alright, there you go. Alright, so moving on, we found our horizontal asymptote. Now there are no slant asymptotes. Slant asymptotes occur in special cases, and we're not going to worry about that right now. Alright, vertical asymptotes. Alright, E, F, vertical asymptotes occur. Vertical asymptote definition is where the limit of f of x as x approaches a number equals a number over 0. Alright, which is basically a domain restriction. Alright, A is a domain restriction. But, we've already, you can tell by looking at the function. You can just tell by looking at the original function right here, what's going to make this a number over 0? Well, 2 and negative 2. 2 and negative 2. And how would you do that? You would just simply set the bottom of the function equal to 0. For example, if you had 1 over x squared minus 81, your domain restrictions would be 9 and negative 9, and your vertical asymptotes would be x equals 9, x equals negative 9. So there you go, that's a perfect example. Alright. So, alright, oops. Alright, so basically the limit as x approaches 2 of f of x gives you a number over 0, and limit of f of x, we're talking about the original function here, x equals negative 2 gives you a number over 0. So x equals 2 and negative 2 are vertical asymptotes. Okay? Alright. Now, we need to state the domain. Okay? I wish I could scroll. We need to state the domain. We've already basically found the only domain restrictions. So it's continuous everywhere except for those vertical asymptotes. Alright, EF, don't want to go that far. Okay, what are you doing? Alright, oh yeah, EF, G, here we go. So your domain is all real numbers, but x cannot equal 2 and negative 2. Alright, how do I know this? Oh my goodness. Well, you found the vertical asymptotes up here, right? It's not a function of the vertical asymptotes. Alright, so now let's go about making our super duper sign chart and graph. Alright. Alright, so here we go. Alright, so from negative infinity to infinity, alright, we have the following. We have a lot. Let's start with our our first derivative critical points are negative 2, 0, 2. Okay. Second derivative, gotta get rid of this. Second derivative, negative 2, negative 1.5, and positive 1.52. Alright, now based on the first derivative, we go increasing, increasing, decreasing, decreasing. Okay? So let's do that. Now we're increasing as well here, and increasing as well here, because if you remember from the first derivative, it was increasing to the left of 0, and it was decreasing to the right of 0. So on each one of these little intervals, it's going to be decreasing. Alright, let's look at the concavity. Essentially, between these two, it was concave down. Okay, concave down. And then it was concave up right here and here. Okay. Okay, yeah. Just double checking something. I have a sneaky suspicion that I did something wrong. Okay. Alright, anyway. Alright, so we're concave down right here. So increasing concave down. Oh, concave up right here. And then concave down right here. And then concave up. Alright, so let's list our intervals. Negative 2 to infinity. Oh, sorry. Backwards. Negative infinity to 2, negative 2, negative 2 to negative 1.52, negative 1.52. Oh, that's sloppy. Negative 1.52 to 0, 0 to 1.52, 1.52 to 2, and then 2 to infinity. It's a lot of intervals. Crazy. Alright. Now, after we made the sign chart, we're ready to graph. Okay, so we need a big old graph. Oh, you know what? I think I'm just gonna steal the graph from the next page. Well, maybe I'll steal the graph from, I don't know if I have a graph to steal from anymore. Let's see. Maybe I can copy this one. Alright, let's see. Alright. I never paste where I wanted to paste. I always paste somewhere ridiculous, like up here. Seriously, doesn't mean no good up here. Okie dokie. Oh, there you are. game of Where's Waldo. Almost there. Alright, so here we go. We need this graph to be really, really big. Alright, so we've got a lot of important points here. My important points are mainly, well, let's just look. Oh, shame on me. Let's take a look at the sign chart. We need to label these critical points or you know, or inflection points, or neither. Now this is a critical point. Alright? Now this is an inflection point because it went from concave up to concave down. This is not an inflection point. Alright? This is a critical point as well. Alright, inflection point. And this is a critical point. Now this is not a max or an extrema because it's a domain restriction. Alright, this is not even part of the domain. I hope you all understand that. So let's go ahead and let's just go down the list. Let's start with the vertical asymptotes, -2 and 2. And we're just gonna kind of make. Ooh, can't draw straight lines very well. All right, let's redo that. All right. Alright, so there we go. Nice vertical asymptote there. Alright, right here, vertical asymptote. Alright, so we've got our vertical asymptotes. Let's check out the horizontal asymptote. Alright, we know there's a horizontal asymptote of y equals -2. So let's make one. So let's keep going. We know there's a y-intercept at -2.25. So right about here, -2.25. I'm going to change colors to make sure it looks good. Alright. And there's x-intercepts everywhere, I bet. I don't know. X-intercepts where? Positive and negative 2.121. So where is that at? Alright. So those x-intercepts are basically here and basically here. They're very close to positive and -2. So positive 2.121 and -2.121. Okay, so there you go. Alright, so we got that. Alright, now we have a relative max at f of 0 equals -2.25. We've already done that. Alright, so pretty much all this information was to make this sign chart. So let's go ahead and use the super duper sign chart to do this. Now we're increasing in concave up. The only way to be increasing in concave up is to go like this. It doesn't matter how you work this to the left of -2. You have to have the graph looking in such a manner to be increasing and concave up. Notice it's opening up, right? It's opening up forever and forever. Now, this next one, let's see. This This next one's very interesting because I don't know why it says that it's concave up on this interval. So actually I'm not quite sure what the problem is right here, because it should not be concave up, but maybe it is, or maybe that's a glitch in the graph, because if I look at the graph, and I'll show y'all real quick. Alright, so looking at the graph, it's interesting because the graph shows concave down all the way. Maybe if I zoom in, say if I zoom in, if I can see that it's concave down. Let's see. I can't move it. Trace. Oh, it's not moving it. So let's see. Window Ymin negative 0.5. Ymax 1.5. I just want to see the bottom of the graph, and okay, so yeah, it's definitely concave down all the way, guys. So I'd be interesting to see who can find the mistake I made to have that 1.52 and that negative 1.52 in there. I knew I made a mistake somewhere, but I had already started filming, so I couldn't catch my mistake. So that shouldn't be there. I'm fairly sure of it. So actually, these points right here are not. They say it says they're inflection points. They're really not, because this should be concave down. All right, and so that's not an inflection point. All right, that would be a critical point and an inflection point. All right, and this says concave up. It's not. It should be concave down, and that's not a critical point, or sorry, not an inflection point. That's a critical point and an inflection point. All right. So with that said, there's no need for these, and I'd be interested for y'all to find my mistake. I probably just simplified wrong. But anyway, at any rate, all right, from -2 to 0, we're increasing concave down. And the only way to fit in there is to go like so. Okay, notice concave down, increasing from left to right. And then we're decreasing concave down. Oh, sorry. Alright, so notice concave down, decreasing from left to right. And then we're decreasing concave, well, it should be concave up. Well, no, that's concave down because it's 2. After 2, we're decreasing concave up. Okay. Oops. Alright, so there we go. Oh my goodness. Alright, so here we are decreasing concave up. Now that's about it that you have to do for this problem. The problem on your take-home quiz is much easier than this problem because it only has one vertical asymptote. So there's a lot less involved. I'm going to scroll up and see if I can't quickly find out where I messed up. But that's pretty much it for this video. Okay, I will see y'all later. Talk to y'all later. No, I'm trying to find out where I messed up.
Okay, because I know the store was going to help me go on this.
Okay. I'll be done in just a second. Yeah, I can do that next. I seriously, alright guys, I seriously cannot find out where I messed up on my second derivative that got me those silly points right here, negative 1.52 and positive 1.52. So, apparently I need to get checked or something, maybe. I just seriously cannot find out where my mistake is. If y'all can find it out, that'd be great. I'm sure there'd be some extra credit involved there. But anyway, I'm going to let y'all go, and thanks for following this. And if you can find that mistake in there as to why I don't know why that's messing up. As to why this is wrong, I'd be happy to know. Alright guys, take care, talk to you later, have a good weekend, bye.